This video is part of our WATS series on static equilibrium and provides an overview of inactive versus active equilibrium. To explore the full tutorial experience, including extended lessons, quizzes, and supporting materials, visit the website linked in the video description. In the first part of this week's session, we will introduce the core concept of static equilibrium, providing the foundation for more detailed analysis. Let's begin with a basic, but very important, question. What does it actually mean for something to be in static equilibrium? To answer that, we'll compare two different kinds of situations. First, picture a crate sitting quietly on a floor. No one is touching it. It's not moving. In the vertical direction, the crate is in static equilibrium. Its weight acts downward. The floor pushes back with an equal and opposite normal force. These vertical forces cancel each other out. However, in the horizontal direction, the situation is different. No one is pushing it. There are no horizontal forces acting on it. So it is not resisting any horizontal motion because none is being applied. We can say the crate is in partial equilibrium, balanced vertically but unconstrained horizontally. Now, consider what happens if someone pushes the crate horizontally. The push introduces a horizontal force. If this force is not balanced by another horizontal force, the crate will begin to slide. In this case, the crate loses its equilibrium as the horizontal force is no longer zero, resulting in motion. So, the crate is in partial equilibrium, balanced in the vertical direction but unconstrained in the horizontal direction. Now, let's consider another scenario, a traffic light mounted on a cantilever pole. Imagine a steel cantilever pole fixed firmly in the ground, extending over a road, supporting a traffic light at its free end. The traffic light introduces a downward vertical load due to gravity. Without anything to resist this load, the pole would rotate downward or tip over. But it doesn't. Why? Because the base of the pole provides both a vertical reaction force and a resisting moment to counter this load, keeping the structure in place. Now consider the wind pushing against the traffic light. This introduces a horizontal force, trying to push the pole sideways. Again, the fixed base resists this with a reaction force and another resisting moment, keeping the pole from moving. Together, these reactions at the base prevent both rotation and horizontal sliding, maintaining active equilibrium. This is the kind of active equilibrium that structural engineers care about. Forces are present and constantly acting, but they're in balance. The system remains still, not because nothing is happening, but because all the happenings cancel each other out. What is rigid body motion? Rigid body motion refers to movement of the entire structure as a unit without any change in shape. There are two main types. Translation: the whole body slides in a straight line. Think of the crate sliding on the floor. Rotation: the body pivots around a point, like a door swinging closed on its hinges. In both cases, the object keeps its shape. Only its position or orientation changes. So, when we say a structure is in static equilibrium, we mean it's not translating, not drifting sideways or shifting forward. It's not rotating, not pivoting or tipping. In other words, the forces and moments acting on the structure are perfectly balanced to prevent rigid body motion. The bottom line: in structural analysis, we study active systems, structures under real loads that remain still because the forces acting on them are in balance. Not by chance, but by design. These systems resist motion not because nothing is happening, but because everything is working together to maintain equilibrium. And here's a key distinction. When we talk about stability and equilibrium in structures, we mean the active kind, not the passive kind. A crate sitting on a floor, untouched, may be in passive equilibrium, but if we gave it a push, it would move. That's why, from a practical engineering perspective, we often classify such passive systems as unstable, even if they're technically in equilibrium. Structural stability means a system can resist potential movement. It has the internal mechanisms, reactions, supports, connections, to hold its ground if and when loads are applied. So for engineers, it's not enough that a structure simply stays still. We need to know why it stays still and whether it would remain still under real-world forces. That's the essence of active equilibrium, and it's the foundation for everything we'll study in this module. In the next section, we'll take a closer look at the types of supports that make this kind of balance possible and how we represent them using reaction forces.